power plant requires 16.36 times 10 to the 6 joules of input fuel energy to produce 1 kilowatt hour of output electrical energy. Find the efficiency rating of the power plant and calculate the heat rate of the power plant. So the givens here were that 16.36 e to the 6 joules. That was called input fuel energy, so we're going to say EN. And so 16.36 e to the 6. I know that's energy because I was told that, and because the units were in joules, so 2 clues. And then output electrical energy, so E out, the stuff coming out of the plant and being sent to the customer, is 1 kilowatt hour. Again, I see kWh. I know that's an energy unit. Little hint. So very helpful to be familiar with the wide variety of energy units that are out there: calories, joules, kilowatt hours, horsepower hours, BTOEs, BTUs, quads. There's a lot, but you'll develop a feeling for them all. We were asked in part A to find the efficiency. Hopefully you remember from the reading that the symbol for efficiency is that funny looking thing. That is the Greek letter eta. It's supposed to look kind of like a cursive uppercase N, but it is eta, E-T-A, is eta for efficiency. And then part B asked us to calculate the heat rate. There is no symbol for heat rate. We just write HR, shorthand, heat rate. And so what's going on here? Well, the solution method. What happens is we've got input energy that's put into a power plant. We weren't told what type of power plant this was. It could be coal. That might be input energy in the form of coal that's going to get burnt. It could be the input energy in the form of natural gas. Like it goes into the plant, and some electricity comes out. And not all of the energy that goes in gets turned into electricity. That plant is going to have some waste energy. It doesn't lose it so much as it just converts it to things that we don't want it to convert it to. Typically that's heat. We call that waste heat. And so we calculate the efficiency of a plant by saying, well, what percentage of the input turned into the usable stuff at the output? And so the efficiency of a conversion process is the usable energy output by the process, in this case the process is our plant, divided by the amount that we put in, right? And the input energy always has to be bigger than the output energy. So this number should be 1 or less, and it's only 1 if the system is perfect, which in the real world is not possible. So in general, this fraction should be less than 1. So we know to calculate the efficiency of this plant, eta, man, that's a terrible eta. Sorry about that, everybody. That's embarrassing. Eta, that's better. We need E out over E in. That's going to give us a decimal. We usually like to write efficiencies as a percentage. It's 50% efficient or 25% efficient. So we're going to multiply that by 100 to get our answer. And we were told that the input energy, which is the fuel that is being combusted, is 16.36 e to the 6 joules, and the amount of electric energy that came out over that same period of time was 1 kilowatt hour, 1 kWh. Clearly we got a little bit of a problem here. kWh and joules, you can't directly divide those. We've got unit inconsistencies here. So we need to do a conversion. I'm going to go ahead and say that there are 3.6 times 10 to the 6 joules in every kWh. If I throw that in the numerator, we can see kWh cancels and joules cancel. Now we get no units, which is good because efficiencies shouldn't have units in them, right? It's a fraction, so the units are going to cancel. It's a dimensionless fraction. So n here is going to be 0.22. no units because they all canceled, so we get 0.22 times 100 is equal to 22%. Right, so that's the efficiency of this particular power plant, which is pretty realistic. So that was part A, by the way. Sorry about that. So hopefully you get the concept of efficiency. In power systems, we often write the efficiency of the system instead of writing it in terms of efficiency like you're used to seeing. We write it in terms of how many BTUs of input energy are required to produce 1 kilowatt hour, and that's called the heat rate. And BTUs are chosen because that's the most common unit that fuels are measured in. So coal, natural gas, whatever you're burning to produce electric energy, usually you know the BTU content of the fuel. So that's why heat rate uses that. But the formula for heat rate is if the system was perfectly capable of, or 100% efficient at conversion, we know that there are 3,412 BTUs per kWh. That's just the heat content of a kWh, or just think of it as a conversion unit. 3,412 BTUs in a kilowatt hour, or 1 kilowatt hour is equal to 3,412 BTUs. It's just a conversion efficiency, right? So then what we do is we just divide that by the efficiency right there. So we put eta in the denominator of that fraction, so we get 3,412 BTU per kWh. But our system's not actually 100% efficient, it's only 22% efficient, so we're going to divide by 0.22, and that means we get 15,509 BTU per kWh as our heat rate. So every 15,509 BTU of input fuel we put into this system, we're going to get 1 kilowatt hour of electric energy out of it. And that's very common in the power systems. Unusual in other branches of engineering as far as I'm aware, but very common in power systems is to present efficiency in terms of the heat rate instead of the percent efficiency.